right, we're waiting for trying to get students to show up. I was here 10 minutes early. Let the record state. But anyways, got lots of fun activities for today planned. I actually do, so don't worry. It'll be worth your time. But, so, alright, we're left off at a molecular orbital theory, and I'll give you this equation, and all you have to know is how to use it for one homonuclear diatomic that only has sigma and sigma star. Okay, and the bond order is number of bonding minus the number of anti-bonding divided by 2. So, for instance, the hydrogen atom, or hydrogen molecule here, if there's 2 hydrogens, there will be 2 bonding here, 2 bonding electrons there, 0 in the anti-bonding, and that's 2 over 2 or 1. And for like helium 2, there's 2 bonding and then 2 anti-bonding. You can tell the anti-bonding because it's got the star. It has this star on it. So the anti-bonding has the star, and then the bonding minus the anti-bonding divided by 2. So like if it's helium, it's like He2, He2 plus. It would be like this situation where, actually I gotta say I have it down there. He2 plus is like this, where you have 2 bonding minus 1 anti-bonding by 2, or bond order of half. Oh yay, whoa. We're up! Wow. The party can start. So that's all you need to know to do in the final. So if you can count the number of bonding, the bonding are the ones that do not have the star, the ones on the bottom, the anti-bonding, the ones with the star on top. And if you can do the number of bonding minus the number of anti-bonding divided by 2 for a diatomic homonuclear, so same atom, you can, it's all you need to be able to do. Is that cool? All right. I forget, you might have to know if it's if there's unshared pairs. You have to know somewhere that's the unshared pairs is a paramagnetic versus diamagnetic. But, so like if you have orbital energies, this is paramagnetic and that's diamagnetic. Okay. I'll show you in a second. So, all right, so that's the end of the stuff for the test. Now this is where we left off. So we talk about S. So let me go talk about S. So S orbitals can constructively interfere to form a bonding orbital, and they can destructively interfere to form an anti-bonding orbital. So p orbitals can do the same thing. They can form a sigma bond. In this case, the blue is positive and the red is negative, or vice versa. I think it makes more sense for the blue to be positive. That's the sign in the wave function. And now the p orbitals can also, 2 of them can form sigma bonds, and then another set can form pi bonds. And the pi bonds, so remember, sigma bond is along an internuclear axis, so between the nuclei. Pi bond is above and below. So the bottom one there is the bonding orbital. That's best to overlap. The top one is in the anti-bonding orbital, where it has bad overlap. And then this one is just the same thing, just rotated 90 degrees. So, now, here are the second period P blocks molecular orbitals. So, if you look at boron, diboron, it has 6 electrons, so 2 sets of 3. 1, 2, 3, 4, 5, 6. And this is when you populate them. It's the same thing as we saw with chapter 8. And these they degenerate the same energy orbitals. So we populate them one at a time with parallel spins. That's known as Hund's rule. And so this molecule here is paramagnetic. So this will respond to external magnetic field. Dicarbon will not, because everything's paired. Same thing as dinitrogen. Dioxygen will, fluorine will not, neon will not. And oxygen reacting to an external field is something that molecular orbital theory predicted, but Lewis theory did not. So, but I want to talk a little more about oxygen. Oh, and one more thing to note. For the first three, the pi bond is lower energy. And the later three, the sigma bond is lower energy for the p orbitals. That's just because of the, here specifically it's the Zeeman effect, it's the magnetic field. But if you go and do the calculations, this is what it ends up doing, but that's above and beyond this course. So it's just, if you're wondering why this is different than this. Now let's go back to oxygen. Maybe you've heard of peroxide, most people have. You never heard of peroxide? Hydrogen peroxide.
Oh.
Yeah. Peroxide, this is a peroxide. So when you have this case, that is a peroxide. I was watching a Netflix show this morning when I was eating breakfast, and they're talking about peroxides. It's actually because they're explosive. You can, I guess, terrorists can make peroxide bombs. So there's better explosive materials than peroxide. They're very shock sensitive. So that's one thing about peroxides is you might, if you're carrying your bomb, it might blow up while you're holding it. But then again, if it's a suicide situation, you know, it doesn't matter. But so that's a peroxide. This case here, so this case there, that's known as a superoxide. And superoxides are even more explosive than peroxides. And superoxides are paramagnetic, peroxides are diamagnetic. But superoxides are even more explosive, like I said. And another interesting tidbit. So, O2 plus. Also, N2 plus, those two molecules are what's responsible for the northern lights. So Aurora Borealis and whatever, Australia Borealis or whatever the heck is in southern hemisphere. Has anyone ever seen the northern lights? I have. They're really pretty. Really pretty. So they're kind of green and yellowish and sometimes purplish. But they come from, so here's the Earth, and here's the positive North Pole, so positive North Pole, negative South Pole, and there's field lines that connect them. And when charged radiation comes at the Earth, they get accelerated towards the bottom and the top. And that acceleration can rip off electrons from nitrogen and oxygen in the atmosphere. And also these molecules are now, they're paramagnetic, so they'll respond to the field lines of the Earth as well. So it makes for a pretty light show. And it's going to be harder to see them now because the sun's starting to enter a period of low activity. So you may not be able to see it for, I guess the sun tends to go in 11-year cycles. And we're going in a downward cycle right now. So in another 6 or 7 years, it's probably going to be easier to see them. And the sun's been kind of not very active as of late too. Okay, so this is not on the test, but draw the molecular orbital diagram, determine the bond order of the N2 minus ion. Do you expect the bond to be stronger or weaker than N2 molecule? Is it diamagnetic or paramagnetic? So N2 minus, this is 2 times 5 electrons for nitrogen plus 1 because of the minus 1, so we have 11 electrons. So this is how you'd build it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like so. And now the bond order, this is the number of bonding, and the bonding are there. I should put the bonding. and the anti-bonding are here. So the bonding, there's 8 bonding minus 3 anti-bonding divided by 2, which is 5 halves, which is 2.5. And N2, it's got a bond order of 3. Because it's, I mean, you already know this from Lewis theory, that nitrogen is like that, it's got a triple bond. But if you, this N2 minus, if you remove that electron, you would have 8 minus 2 over 2, which is 6 over 2, or 3. So, from this, the bond is weaker. N2, and since there's an unshared pair, so because of this, this is paramagnetic. Because it's got an unshared pair of unshared electron. So, questions with this?
Where did you get the 5?
From the valence electrons for nitrogen.
Oh, yeah, okay.
So 1, 2, 3, 4, 5. Oh, I went back. So O2 plus, and this is 11 electrons. How many think it's diamagnetic? How many think it's paramagnetic? Yeah, so we got one person playing. So yeah, it's got, you probably already know with an odd number of electrons it's going to be paramagnetic, but it's, you can see it's up there makes it paramagnetic. So you can see it in the pretty northern lights. So questions with this? Okay, also not on the test. What about, so this is heteronuclear diatomics. So hetero means different, so different nucleus, diatomics, two atom molecules. And this is nitrogen monoxide. Here's nitrogen, here's oxygen. And the difference is that the energy levels are different. So for homonuclear, they are exactly the same, because they're the same atom, but these are different. So then the energy levels are slightly different. It skews them a little bit. So then it still forms similar orbitals, but it's not as symmetric. Now, what about here? Now, here's hydrofluoric acid, and this is what Lewis theory predicts. With that, with the hydrogen, then fluorine has 3 lone pairs. Underneath here is the 2s. So what happens is that the hydrogen atom and the one of the p orbitals for fluorine forms a bonding orbital, and then fluorine keeps its electrons already in the 2s and 4 in the 2p. So there are 6 electrons, 2, 4, 6 electrons that fluorine keeps for itself, and then there's 2 electrons that shared in a bond, and which is actually exactly the same thing that Lewis theory predicts. So just because there is a series of orbitals does not mean they have to participate in the bonding. So next thing is polyatomics, and let me go back to the constructive and destructive interference. So this is with 2. So when you have 2 things, so if you have the plus sign, minus sign, minus sign, you can get a big plus sign and a big minus sign there, and then opposites. So if you have 3, so if you have 3 add, or actually I'll just go back down. It's easier to see here. So if you have, this is for ozone, by the way. So if you have 3, you have 4 orbitals you can form from this. So one where you have this situation, I'm saying red is negative, where it's all positive up top. That's one case. You can have this case here where 2 align and 2 don't. So there's that possibility there. And there's also this possibility there and either way for this one you get a node there. So let me go back to the first one. There is a node, and it's the plane of the 3 nuclei. There's a node that runs through the middle of it. A node is an area of 0 electron density. This one has an additional node here, or if it's the other way, there. And then the worst case for bonding is this situation where none of them align. So, like I mentioned, there were 2 degenerate orbitals here, and if the electrons populate this way, this level here, the highest level, this is known as the highest occupied molecular orbital, or sometimes known as the HOMO. So the HOMO is the highest occupied molecular orbital in organic chemistry. And then the next one up, the blank orbital, that's known as the LUMO, the lowest unoccupied molecular orbital. So the HOMO and LUMO. That's important when you get into organic chemistry. And the last topic for this, here is my beautiful picture of hemoglobin. Hemoglobin is much more complicated. It's got 4 iron centers. But either way, it's an iron attached to a big carbon chain. And there's 4 of them in the hemoglobin molecule. And hemoglobin is a very interesting molecule. It's the more oxygenated it is, the better it bonds to oxygen. But it bonds more strongly to carbon monoxide. And I'm drawing it with the Lewis structure there. The carbon monoxide has unoccupied pi star orbitals. So this anti-bonding orbital is unoccupied, and it has the same sign and shape as a d orbital, or I shouldn't say the same. They're very similar. So it's very easy to overlap. So carbon monoxide can attach itself to iron and hemoglobin very, very strongly. And that's what happens for carbon monoxide poisoning. Same thing with cyanide, too. Cyanide works the same way. Cyanide poisoning and carbon monoxide poisoning, they work similarly by the fact that they cause the patient to suffocate. So I've never had either poisoning, so carbon monoxide nor cyanide poisoning, but apparently, well, carbon monoxide, you start off with a bad headache, apparently, and then you get confused, and then you basically die. And the telltale sign for all of it is pink fingernails. So if you find someone with, I mean, I'm pink in general, but, and I mean, it's like bright pink, like bright, really, really like poke at Foodland pink, because they treat poke at Foodland with carbon monoxide. So it's and it works for, it doesn't matter what your skin color is, and it's always the fingernails are really, really pink. And the treatment for carbon monoxide poisoning is to give the patient as much oxygen as possible, hyperbaric if possible. So pure oxygen or hyperbaric, like above, like pressurized oxygen. And also, typically they inject the patient with lidocaine. That's because their hearts, they found by, unfortunately, trial and error that people's hearts have arrhythmia with carbon monoxide poisoning, and then the treatment. So, but it's hard to treat. I mean, it's because it's hard to force that carbon monoxide off of the iron. But that's the end of the stuff. So anybody have any questions? Okay, so I had a couple missing topics. Some of the stuff I covered either in lecture and lab. But I know we covered weak electrolytes in lab. But I know you're in lab. Are you guys in lab? What's that?
We're in Fisher's lab.
Oh, you are? Okay. Yeah. So, well, you did this experiment then. So if you remember the weak electrolytes, so a weak electrolyte, when you put it underneath when you had the lamp and you put them under and the lamp went dim. So non-electrolyte, you put the solution there, nothing happens. Strong electrolyte gets really bright. Weak, it's kind of dim. And it's because it does not completely ionize. So here is a picture. So here is a non-electrolyte. It just has molecules that do not break apart at all. And here's a strong electrolyte. It's something like a strong acid or sodium chloride, some salt that just breaks apart, forms ions. Now here is a weak electrolyte, and okay, you can see that I'm trying to show it mostly stays as a molecule, but every once in a while one pops off. So that's the weak electrolyte, and it's a molecule that does that. So, but I wanted to emphasize that as well. Okay, multiple ionization energies. The noon class had some questions about this one. So let's look at period number 3. We have sodium, magnesium, and aluminum. So sodium, if you look at, so the ionization energy, so here would be the first, and then the second is just huge. If you look at magnesium, same thing, here is like the first. And the second one's going to be a little bigger because as you rip electrons off, the ion shrinks. So it's harder to rip the other electrons off. But then the third one is just huge. And then for aluminum, same idea. This would be the first. Here's the second. And then the third is just huge. And the reason for this is if you look to the periodic table. So when sodium loses an electron, it becomes like neon. So first electron's not so hard to rip off. But then the second one, when it's neon, it's really hard to rip that one off. Magnesium, the first one's pretty easy to rip off. Second one's a little hard in the first, but it's okay. But after 2 electrons, it's like neon. The third electron, it's really hard to rip off. Aluminum, same thing. First one's easy. Second one's okay. Third one's okay, still higher than the first and the second. But then the fourth one, it's a huge, huge jump. So the successive first ionization potential, is this going to let me go back? Huh. That's nice. Usually kicks me off. So, actually, I'm sorry, I drew this one wrong. Third one's still going to be okay. It's the fourth. Sorry. Sorry about that. It's just the next one there. It's going to be just gigantic because it's when it's ripping it off of a noble gas configuration. So, and then hydrogen bonds. I usually talk about this in 162. A hydrogen bond is an intermolecular, so it's between different molecules. And a hydrogen bond is a hydrogen directly bonded to a nitrogen, oxygen, or fluorine. And then there's a stronger than normal attraction. So there can be a hydrogen bond here, 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 and here, but not not that molecule, because there's not an oxygen, the hydrogen is not directly attached to the oxygen, and then it's shown with these 3 dots then between them. So it has to be a hydrogen directly attached to an oxygen, nitrogen, or fluorine. So, and then the last topic, you guys are all in lab, although we use a lot of pipettes. There's one question on the final like this. If you look at a measurement, then you can look at this, and what is this measurement? Well, this is 31, 2, 3, 4, 5, 6. It's between 36 and 37, and you can kind of guesstimate the 10th scale. So to me, it looks kind of like 0.6 or 0.7. So kind of 2/3 of the way up from that, and you can guesstimate up to the 10th scale between that. Although I know we've been using pipettes, and this is kind of one of the things I don't like about teaching chemistry, is that it's kind of outdated. We usually nowadays, or when you do the exact measurements, we just use pipettes, or we just have robots do it. I mean, the only example I can think of is if you work for a startup company that produces a non-lethal product like beer or like soap. Like, then you might hand titrate something. But, I mean, let's say you work for a company that does baby formula. I mean, you're going to be testing the heck out of that stuff. Because if anything is messed up, it's going to be millions, billions of dollars in lawsuit. But if you make a bad batch of soap or a bad batch of beer, you know, who cares? You know, kind of thing. That's like something that's not going to hurt people. It might make your product a little inconsistent, but I mean, if you've ever made beer or made soap, it's not that hard to do, kind of thing. But all right, so what do I have? How are we doing, sir? Anybody have any questions about anything? What I want to do the rest of the period is I want to do a Emporium model. That's where I solve some problems, and the noon class like this. I'm gonna stop the recording.